Okay, let's start. Hi, everyone, and welcome to today's workshop on multi-objective optimization. My name is Matthew Zari, and I will be guiding you through how multi-objective optimization can help tackle complex decisions in real-world industries, especially through the CALIMERO project. Let's dive in and see how optimization can drive smarter, more sustainable solutions. Let me start by giving you a quick overview of what we're covered today. Today's workshop is divided into five key parts. First, a short introduction to multi-objective optimization, and then we will look at the theoretical foundation to understand the logic and mathematical behind it. Next, we will explore various solution approaches from deterministic methods to more flexible stochastic ones. After that, we will dive into some real-life case studies from CALIMERO project. And finally, we will wrap up the final thoughts, and we're going to have a discussion. Feel free to ask questions at the end or note them down for our final discussion. Before we dive into the technical details, let's first get clear on what multi-objective optimization actually is. In this section, we will look at how multi-objective optimization is structured, why it matters, and how it gives us a more realistic and powerful way to find solutions. Let's start with the basic. What is optimization? Let's say optimization is a process of finding the best solution for a range of possible options. That best solution might mean different things, such as lowest cost, higher efficiency, least environmental impact, or combination of several goals. Let's imagine that you want to book a hotel. You are not just looking for any hotel. You want one that is close to the city center within your budget, has a great guest review, and maybe even include breakfast. Or ideally, you just want all of those things. These are the objectives that you may look for while searching a hotel. This is a classic optimization problem, and instead of relying on the guesswork, optimization provides you a systematic way to help you choose the best possible option based on your priorities. So why should we care about optimization in the first place? Because it allows us to make smarter, more informed decisions. Optimization helps us use our resources more effectively and make a balanced trade-off solution between competing goals. Think back to the hotel book example. Imagine you trying to manually compare hundreds of hotels across price, distance, amenities. It's going to be very difficult, but by using the optimization engine, you can have the best options based on your priority. The same logic applies in industries. Companies use optimization to plan supply chain, allocate budget, schedule manufacturing, and even route delivery trucks to save fuel and time. For example, logistic firms like UPS use route optimization to save millions of gallons of fuel annually, cutting both costs and carbon emissions. Finally, optimization transforms complex, messy decisions into structured models that we can simulate, analyze, and improve. It shifts decision-making from guesswork to evidence-based strategy, and that is why it's so powerful. Now that we know why optimization matters, let's quickly look at how it works. Every optimization problem has three main parts, as you can see over here. First, decision variable, the things you can control, like budget, location, or star rating in a hotel search. Second, objective function, the goals that you're trying to achieve or optimize, like minimizing cost or maximizing quality. That's the constraints. The limits that you have to work within, like budget, availability of time, distance to store or the center. In the next few slides, I will talk you through each part and explain them step by step. First, we're going to talk about the unconstrained and constrained optimization solution space. We usually break optimization problems into two types, constrained and unconstrained. Most real word problems fall into category of a constraint optimization, where your decision must respect a specific constraint or boundaries. Think back to the hotels again search. Hotel search, you may want a five-star luxury experience, but actually you constrained by several things like your budget, available date, and so on. In fact, constraint makes the problem more realistic. While they can add complexity, they can also help you to find a solution faster, more effectively, and efficiently. Just you can see over here in the picture. To build a good optimization model, you need also to know what type of decision variables you're working with. Some are continuous, like time or temperature. They can take any values. Others are discrete, like integer numbers, binary, categorical. We have also deterministic ones with fixed known values. Some are uncertain, like weather or demand, and some are dynamic, like inventory, changing over time. Knowing that what decision variable we are dealing with, it helps you build a smarter optimization model. In optimization model problem, we have two kinds of objectives. Some we focus on one objective, that is single objective problems. For example, in the image on the left side, we have a single objective problem. It's like booking a cheapest hotel. You just insert values in your decision variables and evaluate your goals, like minimizing costs. At the end, it gives you a clear best result if you meet the constraints and the boundaries. But often we are dealing with multiple goals, that is multi-objective problems, like wanting a hotel that is cheap, close, and comfortable. In this case, there is no single perfect solution. As you can see on the right image, instead you're getting a set of trade-off solutions. Now that we have covered the basic structure of optimization, it is time to dive a bit deeper into the theoretical foundation of the multi-objective optimization. In multi-objective optimization, one key thing to understand is how your goals interact. There are three common types. The first one is conflicting objective. This is a most common one. Improving one goal makes another worse, like wanting a hotel that is both cheap and luxury. Usually, you cannot have them at the same time. The second one is a compatible objectives. Here, improving one goal helps to improve another one. For example, writing a product review might help reduce energy use by helping others make smarter choices. And lastly, we have independent objectives. Those goals don't really affect each other, and they don't have any connection, like improving user experience in-app and reducing machine downtime in the factory. They are not actually connected at all. So you can optimize them separately in different space of the solutions. As I mentioned, in multi-objective problems, we often end up with many competing solutions, each better in some way and worse in other. We have two common concepts over here. One part of dominance. We say one solution dominates another when it's clearly better at least one goal and not worse in other of others. The second one is part of front. The part of front is a set of solutions that aren't dominated by any others. In other words, they represent the best possible trade-offs. As you can see in the image, the red point on the part of front dominate the green and the blue points because they offer better or equal values in both objectives. Okay, as we mentioned, multi-objective optimization doesn't give you just one answer. It gives you a set of good options, solutions. You might be wondering then if those solutions are optimal, who's going to pick the final one? Which solution fits best based on their preferences. Sorry. Do you have my screen? Okay. Which solution fits best based on the preference, priority, and constraint like budget, regulation, or technical feasibility. Now that we have covered the theory, let's move on how do we actually solve the multi-objective optimization problems. When it comes to solving multi-objective problems, we usually use the two main target methods, deterministic and stochastic. Deterministic approaches are rule-based. If you give them the same input, they will always give you the same result. They work very well for smaller and well-defined problems. On the other hand, the stochastic methods use randomness. They are great for complex, exploring big problems where deterministic methods might get stuck in local solution or take a lot of time. Next, we will take a look at some of the most common techniques in the both groups. In deterministic approach, depending on the number of the objectives, we use different deterministic approaches. For single objective problems, we use classic algorithms like simplex, branch, and bound, and direct. They work well when they are just one goal. But with the multiple objectives, we need a special strategy to handle the trade-off solutions. The three common deterministic methods, as you can see over here, are rate sum method, epsilon constraints, and brute force. Since we are focusing on multi-objective problems, we will take a closer look at these methods in the next few slides. And they are very simple and efficient, but they have some limitation, and which we'll see in the further slides. Let's start with one of the most simplest and most common methods, the weight sum method. The idea is pretty straightforward. You combine all the objectives into one by giving each weight based on how important it is. It is easy to use and give direct control over a trade-off solution, but it has some little bit limitation. It has a limitation on downside, like it can miss parts of a Pareto front. It requires you to know the right weight in advance, which isn't really realistic. And sometimes you need to normalize objective if they use different units. Next is epsilon method, or epsilon, so also called epsilon constraint. Unlike the weighted sum, this method keeps one objective as the main focus and turn the others into the constraint with the upper limit. It's great when the weights are hard to define or when you are dealing with a tricky trade-offs. You can explain different solutions by adjusting those epsilons. However, we have also some downside over here as a previous method. You need to know what limits make sense, and it takes a lot of time to build a full Pareto front, especially when you have a big problem. So that is not very, very recommended to use the epsilon constraint for big optimization problems. Now let's talk about the brute force method. It's very super simple. You just try every possible combination and pick the best one. It guarantees the best result, and it's great for small problems or testing other methods. But the downside are it doesn't scale. As variable increase, the number of combination explodes. That is why brute force is mostly used for tiny optimization problem, or when you just need a quick validation for your result. As you can see over here, we have a typical travel sales person problem, optimization problem. Here we have a 24 possible path. We're going to exclude 12 of them because those solutions are mirror duplicates. And after that, we're going to write down all of the solution, and we're going to calculate the total cost of each one. At the final, we're going to choose the cheapest one. In this case, the optimal route is A to D, D to B, B to C, C to E to A, which the total cost will be 676. Now that we have covered how deterministic methods work, let's switch gear and look at the stochastic method. These are especially useful for big, complex, and messy problems where the data might be uncertain or the search space is too large for traditional approaches. Stochastic algorithms use randomness to explore different possibilities. They don't follow a fixed path, but that is exactly what makes them very good at finding better solutions, especially when dealing with multiple objectives. Many of those methods are inspired by nature, like evaluation, animal behavior, or physics. In the next few slides, we will look at the two main group heuristics and meta-heuristics. Let's first start with the heuristic methods. Heuristic methods are like smart shortcuts. They don't guarantee the perfect answer, but they great for finding good solution quickly. They are usually based on simple rules, gut feeling, or practical experience from the field, let's say, and are super useful when the time is limited or the problem is too complex for exact methods. Some of common methods we can see over here: nearest neighbor, hill climbing, and beam search. The limitation of using this approach is that can easily get stuck in the local optimal and sometimes going to miss the better solution. That is why in more complex and high stake problems, let's say in optimization, we often use more powerful approaches like meta-heuristic, not heuristics. Meta-heuristics are smarter, more flexible framework that guides the search more effectively, often inspired by nature like evaluation, swarm behavior, or physics. Meta-heuristics are great at searching wisely, digging deeper into possible solutions, and managing multiple goals at the same time. Unlike the basic heuristic, they keep a diverse set of solutions, which is really useful when you're trying to find a trade-off solutions. There are two main common type over here, as you can see: trajectory-based methods and population-based methods. We will dive into the both of this next slide, starting with the trajectory-based techniques. In trajectory-based techniques, the algorithms follow by a single solution as it moves through the search space, kind of like a hiker exploring the landscape of on one path at one time. Unlike the simple heuristics like a hill climbing, which only accept better moves, trajectory-based methods are designed to escape local optimal solution and explore more widely. Two common methods we can see over here are simulated annealing, which it allows occasional worse moves to avoiding getting stuck, and taboo search, which uses memory to avoid going in circle, making it great for navigating tricky areas near local optimal. In population-based meta-heuristics, we work with the group or population of the solution. It's of not just only one, like previous one. We're using different multiple solutions at the same time, allowing for diversity and better chance for not getting stuck into local optimal. One of the most widely used types is evaluationary algorithms. This inspired by natural selection, where better performing solutions are more likely to survive and contribute to the next generation. Through the operation, like we're going to use a crossover and mutation. Those are the two methods, like crossover combining part of the two solution, and mutation introducing small random changes. The population evolves over time and gradually improve the quality of the solution. As you can see over here, you have two methods. Lastly, we have a swarm intelligence inspired by how animals like birds and ants work together without a leader. In optimization, we use a simple agent that share information and communicate the solution with each other to explore solution. Methods like a practical swarm optimization and colony optimization are great for complex problems from tuning system to routing and scheduling. These approaches are especially helpful when we need a wide range of a strong solution. As you can see over here in the image, find the shortest path using the pheromones is shorter path gets refined. After that, faster leading more ants follow them, and over time it's going to find the best path emerges through the positive feedback loop, helping to solve the optimization problem efficiently. Now that we have covered the tools and techniques of the multi-objective optimization, it is time to see how it works in practice. In this part, we will look at the real case study from the CALIMERO project, where multi-objective optimization was used to optimize industry production systems. We have prepared two industry sectors, woodworking and textile. In the first step, we need to define our objective and select the right decision variables. In this case, our main goal is to improve the life cycle performance of industrial processes, not just meeting the standards set by European Commission, but to go behind compliance and drive real measurable sustainable improvements. One of the once the objective and decision variables are cleared and defined for each case, the next step is to build simulation model that accurately represent how the real world process behaves. This process allows us to understand how different combination of input affect key performance indicators like emission, energy consumption, and or their resource use. To carry out this assessment, we have used CIMOPRO and Brightway. These tools enable us to connect the simulation output directly to life cycles, sustainability assessment indicators. Then, to identify the best performing solution, we apply multi-objective optimization directly to the simulation module or digital twin of the test process using the objectives that we have defined earlier. Given the complexity of the problem, this process generates a range of the optimal solution rather than a single solution. This allows decision maker to select the options that best fit their context, regulatory requirement, and strategic goals. The final result is to have a flexible multi-objective optimization framework that can be adapted to different industry processes like woodworking, textile, and beyond. It helps to figure out which process parameter matter most, understanding the solution between things like a cost, emissions, and find smarter way to boost overall performance. Here's how the full optimization process framework works. Step by step, we start with the initial set of inputs. This goes to a simulation model that calculates things like energy use and emission. Then we feed this data to the LCA module to measure the environmental and social impacts like carbon footprint or toxicity. Now, next is the optimization algorithm compare this setup to others and create better alternative using evaluation methods like mutation and crossover. This cycle repeats over several rounds, constantly refining the solution until we see the clear improvements. Let's take a look at the woodworking case study from the CALIMERO project, which involves the three main stages. First, raw material extraction, second, transportation, and third is the final product. Once we have a bigger picture, we can start building the full diagram of the woodworking workflow from the harvesting trees to final finished product. It begins with the raw material extraction, followed by drying and screening, and then it comes gluing, and after that, the pressing stage. Finally, the Final product are trim and sand, completing the production process. Based on the manufacturer's input and information, we focus especially on the pressing process. In this stage, the key variable we optimize were pressing time of temperature and glue ratio. After defining the actual problem, it is time to establish the goals. Here, we want to minimize climate change, impact human toxicity, fresh water eco-toxicity, a combined score of minor impact, and OPEX, the operational cost. As we can see, these goals often conflict. That is why we need to use a multi-objective optimization to find the best solutions. To run the optimization, we use the Contactica algorithm, population-based evaluation method designed for multi-objective problems. Here, the basic hints that the algorithm used here, we define the range for variables like pressing time, temperature, and adhesive use. Then we randomly generate a starting group of the solution. Each solution is scored based on how well it meets our goals like cost, emissions, and toxicity. Then best one are kept, combined, slightly mutated, or crossover to create a better version, repeating this over several generations. The final result shows that reducing pressing time and lowering adhesive concentration generally leads to decrease in total emission. At the same time, slightly increasing the pressing temperature improves overall process efficiency without introducing significant downside. As well, we understood that more pressing time with a lower temperature helps reduce toxic emission, particularly related to human and ecological health. Lastly, we understood less pressing time with a higher temperature leads to lower CO2 emission and reduce OPEX. Okay, now I will hand it over to our partner in CALIMERO project, who will walk you through the optimization work done in textile sector.
Good morning, everyone. Thanks, Madi. I'm Maura, and I'm gonna explain you the textile case study. So the process on which we focused is the washing after the sizing, which is indeed one of step after the warp yarns are supplied to the company, and it comes before further treatments like bleaching and so. The next, please. Okay, here it's a schematic representation of the process where we mainly focus indeed on washing after the sizing. This process consists in washing indeed in a big tank that is supplied by the cold water from the network, and the process has also energy inputs. And afterwards, the treated water is released to the treatment system. So why is this process interesting for optimization? It is because there is a heat supply that is provided by the use of the boiler, a traditional one fueled by natural gas. So there is the combustion associated to that. Moreover, after the heat of the process, it's provided through the system, the hot water is directly sent to the treatment without any recuperation. So the heat load is actually lost and there is no resource circularity. So the optimization lays in the possibility of installing an additional device, which is a heat exchanger, that would transfer these heat from the exhaust water to the clean cold one, avoiding or at least reducing the use of the natural gas. So in the next slide, we can see objective to the optimize that are kind of extensive. And so here we are already adopting a different approach from the standard one that would require only a techno-economic optimization to find the proper dimension of a heat exchanger to provide the heat load required for the process. So the novelty that we are introducing, just a second, please, before. The novelty that thanks. The novelty that we are introducing and this project lays in the fact that we are included also social and environmental objectives in addition to the economic ones, which indeed lays in climate change reduction, toxicity reduction, and also minimization of OPEX and costing and maximizing job creation potential. Okay, the next slide, please. We can indeed find and define a bit better the strategy that we adopted. So first of all, we wanted to select one indicator of representative indicator for each assessment. For example, the LCC for the economic assessment and the single score for the environmental one. And once we have that defined, we are going to create the scenarios, meaning scenarios are defined by the different dimension of the heat exchanger device. Where, of course, the bigger the heat exchanger is, the more heat is going to be recovered. But there are also other effects to control over the system, which might be economical, a huger capex, and some modification also for the job creation potential. Indeed, after the scenario is defined, we actually calculate all the indicators in each scenario. And finally, we can apply the optimization method. The optimization method we selected is the discrete epsilon constraint optimization, which consists in a set of acceptable ranges for initial variables, meaning, for example, there we defined budgets for the purchase of the new device and environmental tolerance. Afterwards, we defined the order of priorities between indicators, as the first ones will have a huger impact than the second and the third ones. And this for sure will influence the results. Finally, the epsilon constraint method indeed consists in narrowing the range of the acceptable solution until the optimal one is found. Or a selection of solution as defined. I will come back to this in the advantages of the method, which is indeed easy to implement and also flexible, because depending on the needs, the order of priorities can be changed, and also the ranges can be narrowed or extended. Because as we said, we can have up to one or several solutions, depending on how broad the ranges of definition are. So if they are quite strict, we might find only one solution, but if they are quite broad, there might be a group of solutions. Okay, in the next slide, we can have finally a look of the results. So before having a look to the table, I would like to say that we have calculated all the indicators for the reference scenario, the baseline, which is the one we started from, and then we have recalculated the assessment for the multi-objective optimization. And here we can see the comparison in percentage of reduction of the impacts related compared to the baseline scenario. As ranges of definition that we took before running the multi-objective optimization, we defined a budget for the CAPEX and for the environmental burden, and we wanted to maximize the social benefit. Given the order of priority, we started from the social impacts, which will have the highest relevance, then the manufacturing cost, and finally the environmental impacts. So finally, we can come back to the table and we see indeed we achieved quite impressive significance in the reduction of the environmental burden, especially in the climate change, but also in the toxicity and in the single score, which consists of all the impact categories. Also, the job creation potential showed an increase, so a benefit under the social perspective, and also the OPEX had a minimization as there is lower consumption of natural gas. On the other side, we have the increment of the LCC, and this is due to the investments that we have to carry out for placing a new device in the system. But a next step or further evaluation would consist in extending the system boundaries of the case study within the system boundaries of the company to include additional processes that could benefit of the use of the heat exchanger, and that would lead to even better result, and for sure lowering of the capex and the reduction of the LCC. Okay, I will give the word back to Madi. Thanks for your attention.
Thank you so much, Laura. Sorry, Maura. Let's wrap things up of today's workshop. As the wrap up, let's bring it all together. We started with a big question: how do we make a better decision when there are multiple goals at play? Throughout the workshop, we saw how multi-objective optimization helps us manage trade-offs, not just pick one goal, but balance many and trade off different goals. We covered the basic of the multi-objective optimization, explore solution methods, and we saw how decision makers play a key role in choosing what works best. Most importantly, we look at the real world case study from the CALIMERO project, showing how these tools can cut emission, lower costs, and support more sustainable process in industries like woodworking and textile. In the bigger picture, multi-objective isn't just about the math, it's about making smarter, more sustainable choices. So thank you so much for being part of this session. I hope it sparked some ideas you can take into your own work. If you have any questions, please feel free to let me know. We are happy to help. So I guess we don't have any questions. Hello, Hakan. I can see your question. What about job creation potential? Could you be more specific regarding woodworking, or you talking about the textile? Maura, if you want, you can.
Yes, I'm here. I see Akan is still typing. Will there be more work? Yes, okay. So yeah, the comparison actually showed that despite there will be a reduction of employees that are occupied in the natural gas supply network, the potential employees that would be actively working in the creation and the assembly of the heat exchanger would be higher. So there would be a benefit in installing, in addition, a heat exchanger. I hope this answered your question. Otherwise, I can clarify further. I see you are typing, so I will wait for your question. You give numbers with 4 digits. What are the prediction confidence of the results? I'm not sure I understood well your question. So you mean like a value of uncertainty of the results? For that, we didn't run uncertainties. We can tell that we try to be as accurate as we could be, taking the data from the company and also based on literature reviews. Okay, yes, uncertainties. Yes, and based on literature review, and we documented that. We have to say that, of course, the database, we used Psica database for the job creation potential, which is a bit more general than EcoInvent, for example. So there, the data are a bit grouped more, the data sets are more grouped and more general. For example, when we assess the indirect worker hours and we realize the need on the database, we don't have a specific data set, for example, for heat exchanger, or we don't have one for the machine or the boiler specifically. They are grouped in the same type of data set, so it's a bit harder to distinguish. We encountered this uncertainty with EcoInvent as well, and there we model the heat exchanger ourselves based on literature review and the data available. But we didn't run a comprehensive uncertainties analysis about this case study. Okay. Sometimes a solution might hide the optimal because of noise in the data. Yes, indeed. Sometimes we indeed talked about the suboptimal results because it's optimal for us for the way we run it, but it might happen that exactly the suboptimal one is not perfectly shown. So yes, thanks for your remarks. It's really meaningful.
So
Okay.
if there's no any more questions, then we can call the workshop. Thank you all for joining to this workshop today's workshop. And yeah, thank you so much.
Thank you very much. Goodbye.